This is CPM Precalculus Chapter 2, number 98. Consider the area under the curve f of x is equal to the square root of x squared plus 2 on the interval 3 is less than or equal to x is less than or equal to 5. Alright, so we're looking for, I'm going to rewrite what we're looking for. We're looking for the area bounded by our function f and the x-axis between 3 and 5. Alright, because that's how we write it. So that's what we're looking for, or that's what we're considering. Part A, write out the sums you would need to add up to evaluate the right and left endpoint rectangle approximations for the area using 4 rectangles of equal width. Okay, do not add them up. Leave the expression in standard form. Or in expanded form, excuse me. Alright, so let's go ahead and sketch the graph of f of x. Okay, so I'm going to sketch it here. That's my x-axis and my y-axis here. I can go ahead and use my calculator to help me. So I'm going to turn it on. I'm going to put y equals, and I'm going to substitute this for what I have here. So the square root of x squared plus 2. Close my parentheses here because that's where it opens, and graph. Okay, so that's the graph of f of x. I know it looks like this, right? Like this. And there are arrows on both sides, right? Alright, so sketching it is fine to do it like that. And what I want to look, though, is at the region between 3 and 5, okay? So here's 1, 2, 3, 4, 5. Okay, so I'm looking specifically between x is 3 is this point and x is 5 is over here, right? We're looking for the area in this region between 3 and 5. Okay? So write out the sums you would need to add up. Alright, so if I'm using 4 rectangles, well, I know if I'm going to use 4 rectangles and I'm going to fit them here in these 2 units, each rectangle is going to be half, right? So I'm going to have one rectangle going up to here, right? One here, another one here, right? So the base of each rectangle is going to be half of 1 unit, right? And I can also find the base is equal to the distance 5 minus 3 over the number of rectangles 4, right? And 5 minus 3 is 2 units, and I know this is 2 units in length, divided by 4, and I know that's equal to 1/2 or 0.5, right? So the base length of each rectangle here is 0.5 units, okay? So we want to add up, let me go ahead and put the calculator away. We want to add up the area using 4 rectangles of equal width to approximate this region's area, okay? So we're going to do it once for right and once for left endpoint rectangle approximations. So I'm going to split that up. I'm going to do right, endpoint. Let's do right endpoint first. And what right endpoint is saying to do is to take this rectangle here, right? This is a rectangle, and use the right side of the rectangle, right? Because the rectangle has a right and a left. But use that right side's height to form the rectangle. So the rectangle is going to be this tall. Again, use the rectangle's right side height, right, to form the rectangle. So it's going to be that tall. Use the rectangle's height on the right side. So it's going to be that tall. Use the rectangle's height on the right side. So it's going to be that tall. Right? So using that, my area bounded by f and the region 3 to 5 right, using 4 rectangles, it's approximately, so my first rectangle has base right here, it has length 0.5, so it's 0.5 times the height. Because remember, the area of a rectangle is just equal to the base times the height. So I could even write that here. I have 4 rectangles, and I know that that is just going to be base times height. Let's say base 1 times height 1 plus base 2 times height 2 of the second rectangle plus base 3 times height 3 plus base 4 times height 4, because we have 4 rectangles, right? So that is my area. Let's go ahead and plug in what B is. Well, we know the base for each rectangle is 0.5 units. So the first one is 0.5 times, what is the height? Well, the height here is whatever the value of f, our function, at 3.5, right? So this is going to be times f of 3.5, right? We can go ahead and plug that in, which we will do later when we simplify this to figure out what that is. Okay? Plus, the second one, this rectangle here, we know has, again, base 0.5 and height. So base 0.5 times the height is now basically looking at the function right here. The height is when we plug in 4, right, into f. And that gives us the height of this rectangle, right? So that's going to be times f of 4 plus, let's go ahead, and the next rectangle is right here, right? And has, again, a base of 0.5. And a height we know is going to be the function at 4.5 will give us this height here on the right side. So it's going to be f of 4.5. Finally, we're going to add the area of this rectangle. And again, it has base of 0.5. And height now is whatever the function is at 5, right? Because we have 5 here. So it's going to be times the function at value of 5. So let's go ahead. We don't want to multiply these, but what is f of 3.5? Well, let's plug in f of 3.5. So instead of x now, we have 3.5. Okay? So that's going to be times square root of 3.5 squared plus 2. 3.5 squared plus 2, right? Plus 0.5 times, now we have square root of, again, we're going to plug 4 into f. So with the input of 4, we have 4 squared plus 2, square root of 4 squared plus 2, right? Plus 0.5 times, again, we're going to plug 4.5 into the function. So it's going to be 4.5 squared plus 2. Finally, our last one is just 0.5 times f of 5, again, we're going to plug in 5 there, so it's going to be times square root of 5 squared plus 2. Okay? And it tells us in the in the problem to go ahead and leave the expression in expanded form. So this is it. We're done. I'm going to put a check mark there. But that was just part of it. That was the right endpoint using the right endpoint rectangle, right? Right endpoint rectangles. I'll even say 4. We're using 4 right endpoint rectangles. Okay, so the other part is we want to use left endpoint rectangles. So let's go ahead and say, well, if we use 4 left endpoint rectangles, what is my area going to be? The area between the function bounded by our x-axis and between 3 and 5, right? It's approximately, so looking at the picture now, okay, now we still have the rectangle here with the base of 0.5, but now we're going to use the height going all the way up to where the left side of the rectangle rises up. So it stops there, and you see how this one is going to make it a little shorter, right? And then the next rectangle is going to go up to this left endpoint and make that one shorter. The next one's going to go up to this point. See how the rectangles are shorter in yellow, and this one goes to this point. Okay? So what does that make us have? Well, let me go ahead and write that out. We have 0.5, the base times the height again. It's the same formula, but now we have different heights, right? We have the base is 0.5. You still have the base from here is 0.5. And the height is going to be now f of, well, we're starting at here, so that's f of 3, right? Plus the next rectangle now, well, the base is 0.5 and it has a height wherever, that's f of 3.5 now, right? So it's 0.5 times f of 3.5 plus the next one. Oops, let's look at it. The next one again has a base of 0.5, and this one now has a height, whatever the height is going to be the function at 4, right? And then you can add that along. So 0.5 times our function at 4. And finally, we're going to get, let's go back and look at the picture, right? The height of this rectangle is the height from 4.5, this point. We plug it into our function, get that height, right? And that makes the height of our rectangle. So it's going to be plus 0.5 is the base times the height of f of 4.5. Okay? And again, we know our function f, I could write it right here, f of x is equal to the square root of x squared plus 2, right? That's given to us right here at the beginning. So let's go ahead and plug these values in. So that's approximately 0.5. Well, what's f of 3? Again, we look at our function. That's going to be the square root of 3 squared plus 2 plus 0.5 times f of 3.5, square root of 3.5 squared plus 2 plus 0.5. I can put these in parentheses again, times square root of 4 squared plus 2, right? I'm right here. And then plus 0.5. And this we know is going to be square root of 4.5 squared plus 2. Okay? So this, again, is the expression. Let's not add it up. Let's leave it like that. And again, that's for left endpoint versus right endpoint rectangles. And we have 4 of them. So let's go into part B. Part B says to express each of the sums using sigma or summation notation. Okay? So let's go ahead and we can just go ahead and continue these, right? Let's go ahead and look at this. Let's look at the 4 right endpoints first. What is the pattern here? Okay, so if we're going to use sigma notation, let's look for a pattern here. Okay, so everything stays the same except for the number being squared, right? It goes 3.5, 4, 4.5, 5. Everything else is exactly the same, right? We have 0.5 in front of each of these, right? We have them all square rooted in this part, right? And we have them all squared under this root and plus 2. So the only thing that changes again is the 3.5 goes to a 4, goes to a 4.5, goes to a 5, right? So what does that mean for us? Well, we know that it's a linear series then with this number, right? So that means it's equal to, let's go ahead and start with our variable, I don't know, k. Say k is equal to 1, right? And how many terms? We have 1 term, 2, 3, 4. So that's small enough for me to just count. So I go from k equals 1 to 4. And the expression then is just going to be this thing, but this number is going to change. So it's going to be 0.5 times square root of something that's changing squared plus 2, right? This is the something that's changing. And what is that? Well, that's what we have to go ahead and figure out. So to figure that out, remember, we have a linear series, and it's basically going from 3.5 to 4 to 4.5 to 5, right? So what does that mean that we should do? Well, that means we have a linear series with the form of y is equal to mx plus b, right? Linear, just like our line here. And the 3.54, we're adding 0.5 each time. So that means that slope is 0.5 because we're adding 0.5 to get to the next one, plus 0.5, plus 0.5, plus 0.5, right? So then let's go ahead and solve for at x is equal to the first term, or let's use k, and let's make this a k then. Right, at k is equal to 1, then I know that this linear series is just 3.5, right? So I know mk plus b is equal to 3.5. Plug in what we know. We know m is 0.5, right? We have it right there. We know k is 1 plus b is equal to 3.5. Solving for b, well, 0.5 times 1 is just 0.5. Subtract 0.5 from both sides and we get b is equal to 3.0. Okay, so that makes this equation up here equal to 0.5 is our slope, k is our variable, plus 3, right? That's b. So in here I'm going to write that, right, because this is where my linear series is. It's going to be 0.5k plus 3, okay? All right, so that again was the 4 right endpoint rectangles, right? The 4 right endpoint rectangles produces this summation notation. Let's go ahead and do the 4 left endpoint rectangles here, right? So let's go ahead and say, well, that's equal to, again, we know we can start at k is equal to 1. And we have how many terms? 1 term, 2, 3, 4. Same amount. It's in the form of 0.5 times, it's in the same form, right? We have something squared plus 2. And that something, again, is being, what's happening to that something? We're adding the constant amount, 0.5 each time, right? So that means we have a linear series with y is equal to mx plus b. But instead of x, I'm going to use our variable k. Whatever variable it is, I'm going to put here. M is 0.5 because we're adding 0.5 each time. So when we have when k is equal to 1, we have mx plus b, or mk plus b, is equal to, well, our first value is 3. Okay, so let's plug in our knowns. We have 0.5 times 1 plus b is equal to 3. 0.5 times 1 is 0.5 plus b is equal to 3. Solving for b, let's subtract 0.5 from both sides and we get b is 2.5. So that makes this equal to, right, we plug it back in, we have 0.5 times our variable k plus 2.5. And we could plug that then in here with where our linear series is, 0.5k plus 2.5. Okay? And that here is our summation notation for left endpoint rectangles, 4 of them, right? So this is just the left, and up here, remember, was the right. All right. Okay, so looking at these two, are they pretty different or are they similar? Actually, they are really similar, right? The only thing here that's different is this value here. We have a 2.5 and here we have a 3. So let's go ahead and look at part C. Part C says to explain how the indices, right, that's our index, relate to right and left endpoint rectangles. Let's write down the right and left endpoint rectangle summations, right? So our right endpoint, let's go ahead and copy it, is just going to be the area between F and 3 to 5, right? What did we get? I'm just copying it from here. let's just copy this, right? So I'm going to write that here so we can put them side by side. We had k is equal to 1 times 4 is 0.5 times the square root of 0.5k plus 3 squared plus 2, right? Let's go ahead and check that these are the same. Yep. Okay, so I'm just copying it over here. The left endpoint, so when we did left endpoint rectangles, we got the area of f between 3 and 5 is equal to k is equal to 1 to 4, 0.5 times. Now this time we just have 0.5k plus 2.5 squared plus 2. Alright, so how do the indices relate? Okay, so I just rewrote it so then we can look at the indices. Well, the indices are here. We're going from 1 to 4. We're going to 1 from 1 to 4. So right off the bat, right, our indices are the same, right? But what could we have done this differently? Yes, we could start from anywhere. And what I mean by that is we can go ahead and we could say, well, what if we were to start with the indices 0 for this one? So let's go ahead and write an arrow from that one and say, well, that's equal to, what if I start at indice k is equal to 0? Then I want to go from 0 to 1 to 2 to 3 to be done, right? I don't go to 4 because I have zeros now one place. And it's going to basically be 0.5 times square root of something squared plus 2, right? So again, I'm going to check. I know this something here is a linear series in the form of y equals mk plus b, right? M I know is 0.5. Okay, I'm just kind of redoing this so we can see another pattern. When k is equal to 0 now, right, my first term for my right endpoint, remember, is going to be 3.5 in that. So it's going to be a k is equal to 0. Mk plus b is equal to 3.5. And that's we're gonna solve for b. 0.5 times 0 plus b is equal to 3.5, right? Solving for b, b is just 3.5, right? So this is going to be equal to 0.5k plus 3.5. 0.5k plus 3.5. Okay? So if I'm to change my my indices, remember this question, part C is asking about indices, all I need to do is basically change, right, the linear series part of my summation notation, right, because the rest stays the same. Okay, so doing this, does that change anything? Not really, right? Do I see how these are related? No. But what if I do the second part, right, using left endpoint rectangles? What if I started from k is equal to 0 and go to 3, 0.5 times something squared plus 2, right? Using left endpoint, what is going to be my new term here? Let's go ahead and figure that out. I have y equals mk plus b. Okay, m I know is 0.5. We're adding 0.5. At k is equal to 0, mk plus b is equal to what? Let's go ahead and look at our left endpoint. The first one is 3, right? That's equal to 3. So solving for that, 0.5 times k, we know 0, plus b is equal to 3. Well then, 0 times 0.5 cancels out, so b is equal to 3. And I have 0, well, let's go ahead and write it here. That's equal to 0.5k plus 3, right? Leaving the variable k in. So that's 0.5k plus 3. All right, so when I look at a different set of indices, right, now I'm looking from k equals 0 to 3 instead of up initially we looked at k is 1 to 4. What do I see changes in here, right? I see that, again, this is my left, this is my right, right? This one is my left, this is my right. I see that which ones look the same? Well, let's use a different color. This part is exactly the same as this part right here, right? Let me put the right part here, right? These are identical, right? This is my left hand, this is my right hand, and my right endpoint and my left endpoint rectangle. So these are the same. If I change the indices, that's the only thing that's changing. Using right endpoint, I'm starting from 1 to 4. Using left endpoint, I just subtract 1 from these and I get from 0 to 3. Okay? So that is pretty standard too. So let me go ahead and say that, right? Going from, remember, if we start at right endpoint, from right endpoint to left endpoint, just subtract 1 from the indices, right? Subtract 1 from the start and from the stop, and you have the same thing. You could also go from left, so likewise, you could go from left to right endpoint, and then you just add 1 to the indices. Okay? So from now on, if you ever are given a right endpoint, right, if you get the work to do this, you can immediately say the left endpoint, right? The left endpoint is this down here because you just subtract 1. Okay? If you start down here, right, with right, you could just subtract 1 again to get to left, right? Whenever we go from right to left, we subtract 1 from our indices, right? So we could subtract 1 from here and again go to left. So it could be from k's -1 to 3 using this as our argument. If we go from left to right, so here we have left, we could just add 1 to get here. So I could, instead of doing all this work, I can just say from k is 1 to 4 with this equivalent inside, right? Or I can start from left here, right, and go to right endpoint. I can just add 1 again, so starting from 2 and go to 5 and use the same argument. Okay, so that's just the relationship between left endpoint and right endpoint summations using rectangles. Okay, you just change the indices and you can get from one to the other. Okay, so going from right to left, I want to subtract 1 from the indices, and going from left to right, I want to add 1 to the indices. Okay? Alright, so that ends for us CPM Precalculus Chapter 2, number 98.